Hello and welcome back to Mrs. O'Graham's Maths. Today we are going through a worked solutions video for Level 3 Calculus. It's the 2021 paper for differentiation. So it's Achievement Standard 91578, one of the externals. Okay, 1A starts us off with a product rule. So dy by dx will be equal to, we differentiate the first part, times it by the original of the second part, add on the original first part times by the derivative of the second part, where sine differentiates to cos, but because we've got the 2 inside, that gets multiplied by 2 as well. And we don't need to simplify our answer, we can leave it as so. Right, part B, we've got this function, we're asked some questions about it. So for this function, find the values of x that meet the following condition. So the derivative is equal to 0. That means that the gradient is 0. We want to know where that happens. So we can see we've got this flat bit here. So everything up to 2. So we can say x less than 2 is our first bit. We've got a point where our graph turns here as well. So the gradient will be equal to 0 at 4, and there's nowhere else. Concave up means if we've got a bowl shape that is sitting the right way up. So that's happening on this curve just here. So the whole of that is called concave up. So that goes from 3 up to 6. So when x is between 3 and 6. Right, the value of the limit as x approaches 7. So that's the graph as it comes towards 7. So from the left and from the right, it's coming towards the same point, which is 3. Don't get distracted by there being a hole there and us being given a different value of the actual function there. It's what's happening as we come towards that point. So coming towards x equals 7, we get 3. Okay, part C, we've got the equation of a curve, find the x-coordinates of any stationary points. Lovely, we just need to differentiate and set equal to 0. We have another product rule. So if we differentiate the first part, we get 2, leave the second part alone, and then add on where we don't differentiate the first part, we differentiate the second part. So that would be 2x e to the x squared. And for stationary points, we set this equal to 0. So I'm going to take out a factor of e to the x squared, and we get 2 plus 2x plus 3 times 2x. Well, e to the x squared, just here, it can't equal 0. There's no solutions to that. So it must be the rest of this bracket here. So we've got 2 plus 4x squared plus 6x is equal to 0. We'll just rewrite that with the plus 2 here so we can see a bit more easily. Let's divide everything through by 2. We get 2x squared plus 3x plus 1. That factorizes quite nicely. So x is minus a half, x is minus 1. And just a quick glance back at the question to make sure we've answered it. Yeah, we only needed the x coordinates. We didn't need to include the y one, so we can stop there. Okay, part D. We've got some parametric equations going on. We want to find the gradient of the tangent to the curve at a particular point. So we need to find dy by dx. Now that will equal dy by dt times dt by dx. Right, so dy by dt is equal to, oh, we've got another product rule. So 2t natural log 2t minus 3 plus t squared times 1 over 2t minus 3. So that'll just be t squared over 2t. Oh, no, hold on. So t squared times, it'll be 2 over 2t minus 3, like that. Dx by dt will be 2t plus 3. So back to dy by dx. Okay, so dy by dt we've got 2t natural log 2t minus 3 plus 2t squared over 2t minus 3. And we're going to times that by 1 over 2t plus 3. I'm not going to bother trying to tidy that up. We don't need to. We need the gradient when we're at this point, so when x equals 10. So we'll just use that. So if x is 10 and y is 0, let's use the x is 10 on this bit here so that we can work out the value of t. So I'll just rearrange that a little so it's like this. So t minus 5, no, it would be plus 5, t minus 2. So t will be either minus 5 or it will be 2. Now let's check by putting it back into the y equation. We need y to come out to 0. So if we start off by trying out minus 5, let's put minus 5 into here. We would be doing minus 5 squared times by the natural log of 2 times minus 5 minus 3. We get a problem there because you can't do natural logs of negatives. So let's just double check it. Instead of doing minus 5, let's try the other value we had for t, which was 2. Okay, and we get 0. So t equals 2 gives y equals 0. So we want to know the gradient when t equals 2 is now going to be, we pop it back into all of this up here. And we get the gradient as being 8 over 7. That felt like a lot of work for that one. Anyway, let's move on to E. So our excellence question for question 1. We have a cylinder sitting inside of a cone. So that cylinder's radius could change within the cone, and we want to find the radius that would give us the maximum volume of the cylinder. So if we think about this running a central line down here and the sort of triangle that we can make, that's going to help us out. And I'm going to use r as being the radius of the cylinder. And then the rate that we're looking at maximizing is dv by dr. So we need a way to work that out. We need to be able to set that equal to 0 to find the maximum it could be. So to do that, we need a formula that links v and r. So for the volume of the cylinder, that is pi r squared h for the volume of a cylinder. I'm talking about that being the cylinder just here. Now, at the moment, it's got 2 variables in it. We need to define h in terms of r so that we can differentiate it with respect to r. And h is this height of the cylinder just here. Now, my preferred method of doing this is similar triangles. So if we think about the big triangle that we've got here, where that's 3 and that's 1.5, we've also got a little triangle just here that's similar to it. So that little triangle will have a height of h, and then this here will be, the base of this little triangle will be 1.5 minus the radius. So now we can link those two. So the proportion of h over 3 will be equal to the proportion of 1.5 minus r over 1.5. So h is equal to 3 times 1.5 minus r over 1.5. Well, 3 divided by 1.5 is 2. So that'll be 2 times 1.5 minus r, or 3 minus 2r. So back to what we were doing with our volume formula. This is now pi r squared Now h is equivalent to 3 minus 2r. So that's going to be 3 pi r squared minus 2 pi r cubed. Okay, now we can differentiate it. So dv by dr will then be, well, 3 pi is just a number, so think about differentiating the r squared, so that'll be 6 pi r minus r cubed gives us 6 pi r squared. To maximize, we want to set that equal to 0. So we can take out 6 pi r, and it's 1 minus r. Well, if 6 pi r was equal to 0, then r would be 0. We can't have the radius 0, that wouldn't make anything. So it must be 1 minus r is equal to 0. So r is equal to 1. We'll just say that's invalid, just there. Back to our question, remember, the maximum volume of the cylinder. We're trying to find the volume. So we know that it happens when the radius is 1. So when r is 1, the volume is equal to pi times 1 squared times the height, which was 3 minus 2 times 1. So that's just 3 minus 2. So that is equal to pi. For 2a, we have the chain rule. So we differentiate the outside, leave the inside alone, times it by the derivative of the inside, which will be negative 2x. We do not need to simplify. We'll leave it like that. For part B, we have the quotient rule. So dy by dx is equal to v du, so the bottom times the derivative of the top, minus u dv, so the top times the derivative of the bottom, all over the bottom squared. And to find stationary points, we will set that equal to 0. Now, if we were to bring that up to multiply to solve the equation, that's going to end up being 0. So we just need to worry about the top line. If I simplify the top line, we've got 2x squared plus 2x minus x squared is equal to 0. So we've got x squared plus 2x is 0. Factorize, and we've got the following. So x equals 0 and x equals minus 2. Okay, for part C, we want the equation of the normal. So we'll need to find the gradient and substitute it in for the equation of a line. Okay, so let's start with dy by dx. We've got the product rule again, so differentiate the first one and we get 2x plus 3 times by cos 3x, and then add on, leave the first one alone, differentiate the second one. So if we differentiate cos, we get sine, but it's got a 3 in it, so it's times by 3 sine 3x. And also cos goes to negative sine. So let's pop that in like that. Okay, now back to the question. It's we're doing this where the curve crosses the y-axis. So when it crosses the y-axis, the x-coordinate will be equal to 0. So when x equals 0, dy by dx will be equal to 3 cos 0 plus, so if we pop a 0 into this bit, we will have 2 times minus 3 sine of 0. Well, cos of 0 is 1, sine of 0 is 0, so that will equal 3. Now that gives us the gradient of the tangent, and we want the gradient of the normal. So gradient of the normal will be the negative reciprocal. Now we're going to put that into equation y minus y1 is equal to mx minus x1. So for that, we're going to need the coordinates of a point on the curve. So we'll go back to when x equals 0, we've got the gradient, but we can also work out the y term. So if x is equal to 0, we will have 2 times cos of 0, so that's equal to 2. Now we can substitute it into here. So y minus 2 is equal to our gradient of minus a third x minus 0. So y is equal to minus a third x plus 2. Part D is a rates of change question. So we've got the volume is increasing at a constant rate. So the volume, the rate it's increasing over time is 60. We want to find the rate of increase of the radius. So we need to work out dr by dt. So if we start with the thing we know, dv by dt, what we'll need to turn that into dr by dt, we need a dr on the top and a dv on the bottom so that that cancels to dr by dt. So we need to be able to find dr by dv. We need a formula that links v and r together. So the volume for a sphere is 4/3 pi r cubed. So there we have a formula that links them together. If we differentiate dv with respect to r, we will get 4 pi r squared. So now we can go back to this one. Just going to move it to the side a little bit. And we can then pop in dv by dt is 60. dr by dv is almost this one, but it's flipped over. So we need to flip this. So it'll be 1 over 4 pi r squared. And so we want to work this out when r is 15. So dr by dt will be equal to 60 over 4 pi times 15 squared, which comes to 1 over 15 pi, or 0.0212. And if we just go to check on the units we're using, so the radius is measured in centimeters and the time is measured in seconds, so centimeters per second. So we have a curve, we've got a tangent to the curve, and we want to work out the coordinates of the P where that tangent touches the curve. All right, so I am going to call P AB for its coordinates. We're going to be doing gradients of the curve, so dy by dx, well, y will be equal to, this thing up here is 2x minus 4 to the half. So if we differentiate that, we've got half 2x minus 4 to the minus half, and then times it by 2. So the 2 will cancel with the half, and we've got dy by dx is equal to 1 over the square root of 2x minus 4. Now the gradient of the tangent, we can do in terms of rise over run. So we've got P is the coordinates AB. So the rise is b minus 1. And the run will be a minus 2, so a plus 2. So that'll be b minus 1 over a plus 2. And we can set that equal to the gradient we worked out from the curve at the point P would be 2a minus 4. Okay, so I'm going to try and solve this to work out the a and b parts. So we'll have b minus 1 will be multiplied by the square root of 2a minus 4 is equal to a plus 2. Now I'm going to pause in trying to solve this at the moment because we've got a's and b's mixed up. We can replace b in terms of a by using the fact that y equals the square root of 2x minus 4. So b will be equal to the square root of 2a minus 4. So now we have an equation where I've replaced the b with its equivalent version in terms of a. Next I'm going to multiply out this bracket. Then do a bit of rearranging. You can pause the video if you want to watch what I just did. So A is going to be 10, or A is going to be 4. Now we've ended up with two solutions because at one of the stages in solving we squared. So we need to go back to before we squared, which would have sort of dealt with getting a positive or negative value there to see which one works at this line of the equation. So at this line, if we put 10 in, we'll get 2 times 10 is 20, minus 4 is 16. Square root that, we get 4 on this side. And if we check on this side, 10 minus 6 is equal to 4. Okay, that's looking good. Let's just double check with the other one. A is equal to 4. Then 2 times 8 is, 2 times 4 is 8. Take off the 4 is 4. And we square root that, and we will have 2. But if we do 4 minus 6, then we get negative 2. So that one doesn't work. So A equals 10 is the one that we want. So when A equals 10, B is equal to the square root of 2 times 10 minus 4, which is equal to 4. Therefore, P is the coordinates 10, 4. Okay, so we are on 3A, differentiating. We've got a quotient. So V du, so x squared plus 1 times the derivative of the top. So if we differentiate cot, we've got minus cosec squared x minus u dv, so cot x times the derivative of the bottom, divide it by x squared plus 1 all squared, v squared. We've got the function for a graph here. We've got a stationary point. We need to find the coordinates of that stationary point. So we need to differentiate, find dy by dx. Well, this is 4x to the half here. So that will be 2x to the minus half minus 1. We set that equal to 0. So we've got 2 over the square root of x minus 1 equals 0. So 2 over the square root of x is equal to 1. 2 is equal to the square root of x. So x is equal to 4. And we need the coordinates, not just the x coordinate. So when x is equal to 4, y will be equal to, well, let's put that in, 4 root 4 minus 4 plus 2, which equals 8 minus 4 is 4, and then add 2 is 6. So Q is 4, 6. Part C, we want to know when the function is increasing. That means the gradient is positive. So dy by dx, we've got another quotient rule. So v du by dx, so we'll do x squared plus 4 times the derivative of the top minus u times dv by dx, so the derivative of the bottom, divided by the bottom squared. And I'll just tidy that up. Now for that to be increasing, we need the gradient to be greater than 0. So solving that through, 4 minus x squared has got to be greater than 0. So minus x squared has got to be greater than negative 4. Now picture what that looks like. So a negative x squared looks like this. When does it go above negative 4? So it's crossing these at the square root side of things. So that'll be minus 2 and 2. And so that'll be satisfied when x is between those two numbers, where it goes greater than the negative 4. So it'll be greater than minus 2, less than 2. Okay, we've got the equation for a curve here. Don't worry about this too much, it's just making sure that this equation works. Point P lies on the curve, has x coordinate of 3, gradient of the tangent we're given at that point. Find out what k could be. So let's start by working out the gradient function. So we have the quotient rule again. And then we can put in the information that we've got here. So at P, x equals 3, and dy by dx, if we put x equals 3 into this, I'm going to tidy this up a bit first. That's easier. So we have minus 8k over, it would be 4 times 3 minus k all squared, or let's change that to 12 minus k squared. We're told that that gradient at that point is equal to minus 8 over 27. So let's work that through. We'll have the 8's cancel out, so we get 27k is equal to 12 minus k squared, and I'm going to carry on working through that. So jumping back in, we've done this quadratic, so k is equal to 48, or k is equal to 3 are our possible solutions. Okay, the excellence question. We've got this lamp suspended above a table. The height is adjustable, and as you move the light closer towards or further away from the table, it will change the illumination felt at point P at the edge of the table. Okay, so they've helped us out by giving us the formula for the illumination, with it being proportional to cos of theta and inversely proportional to s squared. We want to maximize that illumination, find out when that maximum happens. Now, to find a maximum, we need to differentiate and set equal to 0. So we'll be needing to differentiate I with respect to the variable thing, which is h. We need to find di by dh and set it equal to 0. So that's our aim. Now, at the moment, we can't do the differentiation because we've got theta and s in there instead of h's. So we need to attempt to replace them with the equivalents in h. Let's start with cos theta. Cos is the adjacent over the hypotenuse. So the adjacent is h and the hypotenuse is s. So I go back to thinking about what I is. So we can replace k with being what we just worked out, that it could be equivalent to h over s. So h over s, and it's going to get divided by s squared. That's kh over s cubed. Now let's see if we can do something about the s. With our right-angled triangle here, s squared will be equal to r squared plus h squared. So s would be equal to r squared plus h squared to the half. If we carry this on, kh could be r squared plus h squared to the 3 over 2. Now what we're trying to prove is this at the end. The fact that it contains h and r in there gives us a bit of a clue that it's okay to have h's and r's in this. So let's carry on with our differentiating now. So if we do di by dh, so integrating this bit here with respect to h, we've got a fairly complicated quotient rule happening. So v times du, so the bottom times the derivative of the top, if we're differentiating with respect to h, minus u times dv, so the top with the bottom differentiated with respect to h will be 3 over 2, reduce the power, and then times by the derivative of the inside, 2h, all over the bottom squared, which will bring it to be a cubed instead of a 3 over 2. If we're going to maximize, that will get set equal to 0. So I know I only need to carry on with the top because this bottom would be brought over and multiplied by 0. Okay, I'm going to try and simplify the top. Right, so I've got down to this far. Now, we've got these factors that are equal to 0. Now, k can't be 0. Because it was the proportional element of making this equation work. So we can't have that equation zeroed out. We also can't have this bit here can't be 0 because s cannot be equal to 0. This right here was the square root of r squared plus h squared, which was our s value. We can't have this hypotenuse of the triangle being equal to 0. So therefore, r squared minus 2h squared must be equal to 0, in which case 2h squared is equal to r squared. H squared equals r squared over 2. So h is the square root of that, so that'll be r over root 2. And let me just double check. Whew! Yes, h equals r over the square root of 2. Goodness, that was a particularly tricky excellent question. Well done if you made it all the way through.